Today we're going to be doing resonance problems. So I have a handout here, and we're going to be doing the resonance structures in analyzing what would be the hybrid, and if we have charges, what is the charge located, and so on. So let's see. I'm copying the structures that I have here in my handout. So this, let's say we have here a negative and that. So, and it says, problem says that you're generating resonance structures. So here we need to remember that essentially you want to be looking for patterns to do resonance. For example, if you have a charge at an allylic position, you can do resonance here. This is the allyl cation. And here, when you do that double bond over there, that now the positive is here. Remember that here sp2 hybridized, sp2 hybridized. This is also sp2 hybridized, but the p orbital is empty. Now you can do that. And we will put that in brackets, and we will say that now the hybrid, you have partial double bond, here partial double bond, and you will have delta positive and delta positive. So this is what is. So you, the charge essentially is in between carbon, say 1 and 3 here. And equally, because the two structures contribute the same to the resonance hybrid. So now we're going to be seeing this and other patterns. Now what we have here in this structure is a lone pair that is at an allylic position. And here, the two positions of the two atoms have the double bond are vinylic positions. So the next one is allylic. So those lone pairs are delocalized. Now here, notice the arrows. Here I am moving in resonance. You move electrons. Here you put in the arrow from the electrons in the pi bond to make a new pi bond. Here I'm going to be moving electrons in a different way. And this structure has two patterns. One pattern is when there is a double bond and the two elements here have a difference in electronegativity. So I'm going to do one resonance structure like that. And I always want to put my lone pairs to kind of keep track where they are. So the first resonance structure that we want to draw will have now this is positive. And now you will have 3 lone pair at the oxygen and that. Now, this is immediately you need to draw this because now you have a lone pair adjacent and a negative and a positive adjacent. So in general, we don't do that. We kind of jump from that structure to the final one that I'm going to be drawing. And that can be done, say, with 2 arrows. So let's do it going directly from here to here. How would you do that? Well, here I'm doing another color. So you will do 1 arrow here and the second arrow over the oxygen. So these 2. Notice now when you're analyzing the hybrid, this really doesn't contribute because you have object is incomplete at the carbon and you have too many charges. So negative, negative, positive. So that's not contributing much to the hybrid. However, this is. And let's compare that. If you were drawing the hybrid of that, and I'm going to use these 2 structures. And the hybrid would look like the following. So you have partial double bond here, partial double bond with the oxygen. And then notice that in one of the structures, you have negative, but now since there is electron delocalization, this is going to be delta negative, so partial charge. And same in the oxygen. So now we have 2 atoms that are sharing that negative charge. However, oxygen is more electronegative than carbon. So this structure contributes more than that. Because of that, we're going to say that the oxygen is more actually delta negative. So I'm going to draw this larger than this. I'm going to make this smaller to signify that this structure contributes more to the hybrid and that the charge is more on the oxygen than it is on the carbon. Because again, oxygen supports better a negative charge. So let's do another structure. What I have here, this is, it has a negative. Notice that I'm adding electrons. I'm going to add it here as well. So this is cyclo penta because we have 5 carbons. Diene, but it's dianyl anion, cyclopentadienyl. So let's do the rest of the structures now. This seems to be too light, so I'm gonna just draw on top of that with another color so we can see better. Hopefully it is better that way. It is. So now let's do the resonance structure. What do we have here? Another pattern. So similar to what we did before, you have a double bond and electrons at the allylic position. So we can do that. If you did this at this structure, you will do moving electrons. Remember, you need to move electrons. And you will do now, not to expand the octet at this carbon, you need to do a second arrow. So I'm going to draw it on top, the resonance structure that results here. So I'm going to have a double bond in that negative here. So this is the allyl anion. So similar to that, we notice that these electrons are at an allylic position. So we're going to move those. And we're going to say, okay, we're going to make a double bond here. And now, not to expand the octet, I need to move the electrons over to the carbon. So I'm going to make the resonance structure. Let's draw that. So now double bonds are in this position. And I have now the lone pair here. Now let's keep moving electrons around. This is again allylic to this double bond. So I can, in all of the carbons actually here are sp2 hybridized. When you see that lone pair that is at the allylic position, we're going to say this is also sp2 hybridized. And so the lone pair is delocalized. So continuing doing what we were doing in the previous structures. So you move your electrons at the allylic position, make another double bond. And now we're going to be moving the electrons over to another carbon atom in the structure. Not so good. That's better. I'm going to do the double bond here, and the lone pair is here. Now, I can still be moving those electrons because, again, electrons at the allylic position. So I'm going to make a double bond here and move the electrons over to the carbon. In the resulting structure, we have double bond here, the one that you just did, and the lone pair here. I can still, well, if I move those electrons over and make a double bond, so notice that I'm still electrons at an allylic position. So I can do this without making a double bond at this position. And now I am putting the electrons here. So let's see all of the structures that we have generated so far. Electrons at this position and here. Okay, so I have 1, 2, 3, 4, and 5 structures. Notice that in the hybrid, the negative charge is actually in any of the carbon of the 5 carbons in the ring. So my resonance hybrid is going to look like here. This is a partial bond, but I can move it so it can have partial bond, partial double bond everywhere. And I will have the delta negative everywhere. In fact, each of these is like 1/5 of the charge that I have initially. So, and it is spread, the electrons are delocalized all over the ring. So these anion actually is an aromatic structure. And later on, you might see that when you work with aromatic compounds. So that's for now, but we're going to continue more resonance